Welcome to the second lecture on multiple object tracking. So remember that we started in the last lecture with the challenges that multiple object tracking gives to us. And these are different challenges than for single object tracking, for example. So in multiple object tracking, we're looking at scenes like this one here, where we have different objects of the same type, different instances of the same semantic class, for example, different pedestrians here walking around. And the main challenge here is that we have heavy occlusions among these pedestrians and pedestrians being occluded also by other static objects of the scene. And furthermore, the appearance of these objects, since they are of the same semantic class, the appearance is often very similar. So any appearance model that we want to build is going to have quite a difficult time at matching the different instances of the pedestrians with each other, differentiating the different instances from one another. So this, of course, can get really tricky when we go to scenes like this one, the Mod 20 challenge of the Mod Challenge benchmark. So here we see really those heavy occlusions and how building an appearance model of an occluded object is actually a challenging, if not an impossible task in the case of this scenario. So today we will focus on algorithms that use the tracking by detection paradigm. So these are algorithms that essentially start from a set of detections. So independently for each frame, you actually run a detector. And detections are usually not perfect, so we can have false positives, false negatives, but they are actually a good starting point to then perform data association. And the data association is essentially the tracking problem in itself, which is actually to find these detections that match from one frame to the next and that actually form a trajectory throughout the video. And of course, things get difficult, for example, in this case where we have this false positive detection, and now our algorithm might tell us that the orange box is actually matching the yellow box in the third frame because they are really close together. The spatial distance is really small. And so we might have here one false positive that is included into a trajectory. Now, same happens with false negatives. For example, we start this green trajectory here, but we have no detection that can actually be matched to this green trajectory in the second frame, and therefore the only thing that we can do is to cut this trajectory and then start it again in the third frame with another identity. So of course, errors in the detections are going to make tracking a harder task, but this is what we're going to tackle in this lecture. So how to actually perform this data association and how to include a little bit of learning also in that step. So in the last lecture, we also reviewed the concepts of online tracking versus offline tracking. So online tracking was the one where you were processing frames as they come in real time, and you can actually not look into the future. So you're trying to make decisions, tracking decisions, identity, linking data associations in real time. And this is, of course, appropriate for example, for robotic applications, but it's prone to drifting. So once you make an error, it's really hard to recover from it. So we discussed some online tracking methods in the last lecture, and in this lecture, we're going to focus more on offline tracking. So this is more suitable for example, for video analysis, where you have access to the whole video and you actually want to retrieve trajectories as reliably as possible in order to then analyze these trajectories for behavior analysis or any other type of task where you actually require reliable trajectories. So in this case, what we're going to do is we're going to process a batch of frames. So in a sense, we are allowed to look a little bit into the future. And therefore, it's a bit easier to recover from occlusions because you can check whether in the next few frames, the target is actually becoming unoccluded and it's reappearing again. So we're going to start from the frame-by-frame tracking mindset that we started in the last lecture. So remember that in the last lecture we were doing frame-by-frame tracking, and so we were starting from a set of detections at frame t, and then we wanted to match those detections at frame t to the detections at frame t plus 1. So remember also in the last lecture that we discussed actually doing some sort of motion prediction to actually have, for example, estimates of where the pedestrian might have gone from frame t to frame t plus 1. So in this case, we're just interested in performing pure data association. So we don't do any motion prediction, we just have a set of detections at frame t and a set of detections at frame t plus 1, and the only thing that we want to do is we want to link them. We want to match the detections at frame t with the detections at frame t plus 1. And of course we can do this on a frame-by-frame basis, right? This would still be online tracking. But the idea would be that I keep matching detections from frame t to t plus 1, then from frame t plus 1 to t plus 2, etc., etc. So this is one way in which you could actually do data association frame by frame. Now, the matching here is the key part. So the question is, how can I actually match these detections at frame t with the detections at frame t plus 1? So what kind of information do I use to match these two detections? So we can, of course, use same technique as we used in the last lecture. We can use, for example, bipartite matching. So we have to define a set of distances between the boxes, the detections at frame t and the detections at frame t plus 1. And this can be, for example, intersection over union between the boxes, pixel distance, 3D distance, any type of information that we have that tells us how close two bounding boxes are, and therefore how likely it is that these two bounding boxes represent the same person. So in this case, we would use, for example, IOU and, or let's say the inverse of the IOU, so the smaller the value, the better. And then we would solve this assignment problem with the Hungarian algorithm that we already presented in the last lecture. So here again, the solutions are unique. We're trying to minimize the total cost. So what we would obtain, for example, from this matrix would be this assignment marked by the red numbers. So the red numbers are indicating the assignment, and you can see here that there's a correct assignment between the red pedestrians, the green pedestrians, etc., etc. So of course, this is still online tracking, right? So we're still processing the video frame by frame. Now, instead of doing the prediction like we did in the last lecture, here we're doing pure data association. So we're matching detections at frame t with detections at frame t plus 1, and then just moving forward as the frames are arriving to the camera. Now, of course, if we do frame-by-frame tracking, we have a series of problems. We cannot look into the future. We cannot recover from errors. So if a detection would be missing from a frame, then we would have to make a decision, and that decision would be probably to end that trajectory. So essentially, all the decisions that we're making are very local because we're just looking at this pair of frames. So the question would be, can I actually do better to recover from errors of the detection step, right? So in frame-by-frame tracking, we're actually very, very dependent on the quality of the detections. So what I would like to do ideally would be not to look at this like local assignment frame by frame, but to actually find the minimum cost solution for all frames and all trajectories at the same time. So I don't want to find the minimum cost assignment for a pair of frames, but for all the frames in the video and for all trajectories at the same time. And so the question is, how can I actually do this? So here's where graph-based multiple object tracking comes in. So the formulation of the multiple object tracking problem as a graphical model. So essentially what we do is we express this problem as a graphical model. And in this case, what we have is that detections are represented by nodes. So we're still following the paradigm of tracking by detections. So we're still going to assume that we have a set of detections as our initial points. So with that set of detections, what we do is we create a node for each detection that we have in a frame. So you see here, for example, that in this frame we have 3 detections and we have 3 nodes in our graph. Then for the next frame we have another 3 detections and we have again 3 nodes in the graph. And now the idea is that we start connecting these nodes with possible connections. So essentially all the nodes at frame t will be connected with all the nodes at frame t plus 1. And these connections will indicate possible trajectories, possible connections between one detection at frame t and one detection at frame t plus 1. And again, we want to do this for all the frames and all the trajectories in the video. So we're going to create this large graphical model that is going to include all the detections in all the frames in the video. Of course, if the video is really long, then we're not going to be able to fit this into memory. But we're going to assume that in this case, we can at least process a batch of frames. And we can fit all this batch of frames, we can put all this information into a graphical model. So after this, the tracking problem is then to find the connections within this graph that actually identify a trajectory. So for example, in this case, we see that if we connect these red nodes in our graph, if the edges between these nodes would actually become active, we would recover the trajectory of one pedestrian. So again, each node represents a detection. So when I connect 2 nodes with a red edge, for example, what I'm effectively saying is that these 2 nodes are representing the same person. And if I would solve for all the trajectories in my graph, it turns out that I would actually find all the pedestrians in the scene. So essentially, for me, finding now all the pedestrians in a scene means finding all the paths in my graphical model. So again, it is important to go over the concepts again, right? So what does each element in the graph represent? So in this case, again, the nodes represent the detections and the edges represent connections between these detections. So effectively, what they represent is a trajectory. And then we have another concept. We have the concept of flow. So you have probably seen in the title that I've written tracking with network flows. So this is essentially the family of solvers that we're going to use to actually find these trajectories in the graph. And in this notation, one unit of flow would actually represent one pedestrian and would actually represent the connections that we do from the beginning of the graph towards the end of the graph. So you can imagine it as sending one unit of flow from the beginning of the graph towards the end of the graph, and that actually represents one pedestrian. So if I'm sending 3 units of flow through my graph, it means that I have 3 pedestrians in my scene. So let's go a little bit more into detail into what kind of algorithm do I actually use to find these trajectories in my graph. So essentially what I need to solve is what is called the minimum cost flow problem. And this is essentially defined as determining the minimum cost of shipment of a commodity through a network. So in this case, our commodity is our pedestrian, and I want to determine what is the path with minimum cost for which I can actually send this pedestrian from the beginning of the video towards the end of the video. So essentially what I want to do is I want to send my commodities, I want to send my pedestrians from the beginning of the video towards the end of the video. That is, I want to see at each frame what is the best assignment, what is the assignment with a minimum cost that will actually give me the trajectories and will actually allow me to recover the trajectories from the beginning of the graphical model, the beginning of the video, towards the end of the graphical model. And so essentially now what becomes really, really important is to define these costs. So the definition says that I want to find the path of minimum cost to send these commodities, to send these pedestrians from the beginning of the video towards the end of the video. So it becomes really obvious that these costs are actually what is going to drive our tracking results. So essentially, the minimum cost flow problem can be expressed with the following objective function. So essentially, it is a minimization problem. And this is really important because, again, what we're going to try to do is we're going to try to assign low costs to edges that we think should connect to detections that belong to the same person. So in this case, since we're solving a minimization problem, low costs is good, means the two detections are very similar. High cost is bad, means the two detections are very, very different and likely do not belong to the same trajectory. And so now what I have for each edge, so you can see here the depiction of the edge ij, is the definition of this cost value, which indicates how similar the two nodes I and j are, and also an indicator function fij. So again, the two nodes represent two detections, and the cost ij, cij represents how similar these two detections are. Low cost is good, the two detections are very similar. High cost is bad. So essentially this cost is what is going to drive our tracking. And I want to insist on this concept that however we define this cost, whether it's IOU, distance between pixel, an appearance model, what we have to make sure is that if two detections represent the same person and therefore should be connected and form a trajectory, then the cost between these two nodes, the cost of the edge that connects these two nodes should be low. And if the two boxes, the two detections, the two nodes represent two different people, then the cost should be high. Now, the only thing that we need to define is the indicator function. So the indicator function fij is going to take value 0 or 1. And 0 is going to mean that the edge is inactive, is not active, therefore the connection between the two nodes I and j does not exist. If the indicator is 1, then it means that this connection is active and actually the two nodes represent the same person, and therefore we are forming a small trajectory. So fij, these indicator functions, are what actually is going to represent our trajectories. And you can also imagine how this optimization problem works. So if the indicator function for ij is 0, then the cost cij will have no influence in the final cost value for our objective function. That means our cost will be completely ignored. So what we're going to try to do, what the optimization is going to try to do, is going to try to activate edges that actually have very low costs. And again, we said low cost is good because low cost should represent detections which are very similar. So overall, our objective function is going to try to activate only the costs that give us the lower overall cost possible. And of course, these connections will give us the optimal set of trajectories, which is essentially what we're trying to find here. So, okay, once we have this notion that one trajectory, one pedestrian is represented by one unit of flow, and I have to send the flow from beginning to end, then I can start defining the other elements of the graph that are going to allow me to actually solve this optimization problem. So far we have defined only the connections between detections, the connections between nodes, and these are represented by these costs that actually tell us how similar two detections are. But This transition cost, which roughly represent distance between detections, distance in appearance, distance in pixel space, or 3D distance, whatever we want, these edges are not the only element in the graph. They're not the only connections that we actually need to solve our optimization problem. So the other thing that we need are what we call entrance and exit connections. So essentially, we need to, at some point in some frame, start or end a trajectory. So we cannot actually assume that all the trajectories are going to start at frame t-2. It could be that some pedestrian actually appears at frame t. So for this, what we actually need to allow is we need to allow a trajectory to start at any node in the graph. And for this, what we do is we create connections from the source node to all the nodes in the graph. So in this case, I'm just indicating these 3 orange connections here, because otherwise, if I indicate all the connections, then this graph would become super dense. But in theory, what we're going to do is we're going to connect the source node with all the nodes in the graph. And this means that our trajectory can start at any point in the graph, at any point in the video. And the same thing we do with what is called the sync node. So any trajectory can end at any point in the video, and therefore we're going to connect all the nodes in our graph to the sync node. And then what we're going to do is we're going to assign a cost to start and end a trajectory. So otherwise, we would be starting and ending trajectories all the time. So we need to add a penalty. Remember that we're solving a minimization problem. So if we put a positive cost in here, and we say, if you want to start a trajectory, you're going to pay a fee. And the same when you end a trajectory. Like this, we make sure that we only start and end trajectories when we're really sure that there has to be a trajectory there. So we have our entrance and exit costs, we have our transition costs, and now the flow has to start at the source node and end at the sync node. So any trajectory will start at the source and will end at the sync node. So now the question is, well, I know that I'm going to pay a fee to start a trajectory, and I know that I'm going to pay a fee to end the trajectory, right? Cost for starting and cost for ending a trajectory. But if my transition cost is actually also positive, right? Because I just said that it represents, for example, a distance between detections. So this is usually a positive value. So now we go back and we look at the objective function, right? This is a minimization function. And now all the costs that I've defined so far are positive. So what happens with this minimization function? So essentially what is going to happen is that my solver is going to give me the trivial solution, which is I don't want to send any flow from source to sync. So I send flow 0, and therefore my optimal cost, total cost, is going to be 0. Because any flow that I send through this graph is going to be positive. So it's going to increase my total cost. So I am pretty sure that my minimum is going to be sending no flow whatsoever. And if we don't set any further constraints about how much flow we want to send from source to sync, then we're going to get the trivial solution, no trajectories are found in this scene. So one thing that we could do is we could say, well, I want to send 11 units of flow. For sure, 11 units of flow from source to sync. Then I could solve this problem and I would get the 11 best paths from source to sync. The problem is that I don't know how many pedestrians I have in the scene. So I cannot define like this, I want 11 units of flow, because there could be 11 pedestrians, 40, 30, or just one. So for example, if I would be analyzing a football match where I know exactly how many pedestrians, how many players, how many referees are in the scene, I could actually solve this problem by setting a number of flow units to be sent from source to sync. But in my general scenario where I don't know the number of pedestrians, this is not an option. So in order not to get the trivial solution of zero flow, what I can actually do is I can add a negative cost, right? So overall, my problem is that any unit of flow that I send from source to sink is going to accumulate a positive cost. And in the end, if I'm solving a minimization problem, I need to have a cost that is better than zero. Therefore, I need to have a negative cost. So what I'm going to do is I'm going to follow the formulation of this CUPR 2008 paper, in which they say, well, let's take each node. Remember that each node represented a detection in our video, and let's separate it into two nodes. Now, the advantage of this is that now I can put an edge in the middle, which is going to be a detection edge. And this detection edge is going to have a negative cost. So the formulation of the detection edge is the one that you can see here. And it depends on this parameter beta I. And this is actually the probability that a detection I is a false alarm. So essentially, the probability that this is not really a detection, but something else. And this is a probability that you can obtain actually from your detector, which basically tells you how confident the detector is that this is actually a pedestrian, for example, or that this is actually a car or whatever object it is that you want to track. So this parameter beta I essentially expresses the confidence of the detector. And the idea is that the more confident the detector is that this is a pedestrian, the more negative the cost for the detection edge is going to be. So a very negative cost means that this detection edge is going to be very, very useful for the algorithm because it's going to allow to make a lot of connections. This is essentially the shape that we will get with such a function. So you see that it crosses at 0.5. So essentially 0.5 is the middle point where basically you're not really sure whether this is a detection or not. And anything below, which means that your detector is very confident, means that you will get more and more negative cost. Okay, so now it turns out that our graph was not as simple as we thought. So we started with this transition cost. So essentially the cost that connect one detection, or let's say that connect all the detections at frame t with all the detections at frame t plus 1. And these costs are positives, and now we have added some negative costs, which are essentially these detection costs, which are actually connections within a frame. So remember that here now these two nodes are going to represent the exact same detection. So we just artificially separated them so that we can put the detection cost there. So then we're going to have the connections from the source to all the nodes. So I didn't depict it earlier, but now I depict all the connections. So essentially a trajectory can start at any point at any frame of the video. And then we're going to have the connections to the sync node, which actually allow us to end a trajectory. And these go hand in hand with the cost of ending a trajectory. So we have, again, a fixed cost for starting and ending a trajectory. So essentially, this all leads to a linear program mod formulation, because this graphical model representation is a way to better see how these trajectories are formed, and it's actually a very nice visual representation. But when we're actually trying to solve the problem, it turns out that we can map all this formulation to a linear program, which is actually very, very efficient to solve. So we want to use a linear program because there are a lot of fast solvers, for example, the simplex algorithm, that are able to find trajectories in, let's say, 100 frames in a matter of seconds. So aside from being really fast solvers, they're also guaranteed to converge to the global optimum, which means that we're going to get the absolute best solution for the graph and for the cost that we have actually defined. So let's look at the actual formulation for the minimum cost flow problem. How can we actually map it into this linear program? So we have the same objective function as before. So remember that we're trying to solve a minimization problem. We have our costs that represent the distance between the nodes, the distance between detections, and we have our indicator function Fij, which is 0 if two nodes are not connected, or 1 if two nodes are connected and therefore create a trajectory. So now what we need to do is we need to add a set of constraints. So we cannot have all nodes connected to all nodes, but there needs to be actually an order in the connections. And this is what is called the flow conservation at the nodes. So essentially what we need to have is that all the flow that is going into a node is sums to the flow that is leaving the node. So essentially here what we have on the left is the case for which we have this detection I, and we have a series of connections that are leaving the detection for the next time frame. So essentially this connection here in blue, remember that they are these transitions. So these indicate the connections between frame t and frame t plus 1. Then we have our detection edge and we have our start of a trajectory edge. And essentially what the flow conservation at the node tells us is that the flow coming from the detection edge plus the flow coming from the start of a trajectory edge, so basically the flows that are going into this node, the sum of these flows needs to be the sum of the flows that is going out. So essentially what we're doing here is that if we have here a detection, right? And this flow is active, this edge is active, so we have one unit of flow going into this direction, then this unit of flow needs to go somewhere. So we actually need to send this unit of flow to the next frame. And at the next frame, the same happens. So we have our connection from frame t to frame t plus 1. And so if we actually have one of these connections which is active and therefore we have some flow going in, then we need to decide whether to activate this detection and therefore this purple edge would become active, or whether to end the trajectory, right? So all the flow that comes in, the sum of this flow needs to be the sum of the flow that goes out of the node. And these are essentially the first set of constraints that we're going to use for our linear program. So I've already hinted at the second set of constraints, which is actually the edge capacities. So essentially what we want is that we want these flows to actually be constrained also between 0 and 1. So essentially, all the flow that is going to come in or out of a node is going to be either 0 or 1. And essentially, this is because I actually want to assign to one detection, I want to assign it one trajectory, right? So imagine that I activate this edge and I say this detection is active, and at the same time, I start a trajectory here. This both means that I had a past trajectory active coming through this edge here, and at the same time another trajectory will be starting through this node. And this is impossible, right? This would mean that this node would actually represent two people. And one of the most important constraints in our problem is that each node can actually represent only one identity. So there can be no overlapping identities in the node. And this also means, of course, that any flow that comes in here, which is going to be either 0 or 1, then has to go out through one of these connections. So these connections, they cannot be all active, right? I cannot connect this node to 3 nodes in the future. This would mean that the pedestrian suddenly divides into 3 people. I want to have only one of these nodes active. And this essentially can be expressed with these constraints, right? So the first constraint is going to be that all the indicator functions are going to be either 0 or 1. So there can be no half values, no 0.5, but actually either 0 or 1, either they're active or not. And at the same time, the flow that comes in a node and the flow that goes out of a node is going to be, again, either 0 or 1. So this paired with the flow conservation at the nodes means that I'm essentially going to either start a trajectory at a node, continue the trajectory at a node, and finally pass along the connection from frame t to frame t plus 1, and at that point again either end the trajectory or continue it with a detection connection. So essentially the flow conservation at the nodes and the edge capacities express all the properties of the problem, of the multiple object problem, that I want to further impose to my objective function. So my objective function, subject to these constraints, actually expresses nicely my multiple object tracking problem. Now I have only one problem, and that is that these constraints actually mean that my problem is actually NP-hard. So before I said that I was going to use the linear program formulation because it was easy to solve, because there were fast solvers. But if we have an NP-hard problem, then this is no longer solvable in a reasonable amount of time, which means that we actually have to work on a relaxation. And this is called actually the linear program relaxation. So the problem before, the NP-hard problem, is actually an integer problem. And what we can do is we can actually relax it into its linear version. Essentially, what that means is that I'm not going to impose the condition that the flow has to be either 0 or 1, but I'm going to put the condition that the flow has to be between 0 and 1. So theoretically, all these values here could take a value of 0.5, while before, with the integer formulation, this was impossible. But now we have lost kind of this representation that if an edge is active and therefore it takes value 1, then it represents a connection, right? So what happens if now f, our indicator function, takes a value of 0.5? Well, it turns out that luckily for us, given the shape of the constraints, which technically means that our matrix of constraints is totally unimodular, when we actually solve the relax problem, when we actually use our solver to find the solution for the linear problem, the relax problem, we still get integer solutions. So this is really nice, right? Because we can use our solver, we can solve the linear program and still get integer solutions, which we can actually use to represent our trajectories. So we get essentially the best of both worlds. And this is because the matrix of our constraints has this unique shape, which actually allows us to get only the integer values as solutions. So our objective function, as we said, consists of more cost than just edge cost. So we had the cost for starting a trajectory, C in, the cost for the transition, CT, the cost of the detection, which is the negative cost, C dead, and the cost of ending a trajectory, C out. And it turns out that if we actually take this formulation, we can nicely map it to a maximum a posteriori tracking formulation. So some of you, if you have taken a tracking lecture, you might be familiar to the map formulation for tracking. And you can actually find a nice mapping between our linear program formulation and the map formulation, the maximum a posteriori tracking formulation, by just taking the negative logarithm of the probability of the map formulation here. So essentially, there is a nice correspondence between the two formulations. So once we have defined our formulation, now I go back to my initial question and I say, Well, now I want to put some deep learning in there, right? I want to take advantage of the power of deep learning and put some of this representational power into my formulation. So one way of doing that, the most direct way, is actually to improve the definition of the cause, right? So I put all my learning power into the definition of the cause. And there have been several works, some works in our group, into how to do that. And lots of people have actually proposed solutions to put distance information, appearance information, all of this condensed through, for example, a neural network into one value, into a cost value. And this is kind of nice, right? But it still has this problem that you actually have just definition of pairwise cost. So the second way of moving forward is to actually make the graph more complex. So essentially to include more connections. Now, all the connections that we had now were from one frame to the next. We can also include connections from one frame to 10 frames apart in case we have an occlusion and we want to recover that occlusion. And this is all included into the linear program formulation. But we can also include other types of connections, like, for example, connections within a frame, between different boxes within a frame. And this is what these works actually study. And the focus of these works is actually to find a solver that can deal with that type of connections. So when you start making this type of connections, you can no longer use the linear program formulation. And therefore, you need to actually devise a solver that can handle these complex graph structures. But what would be really nice is if we could actually do more learning, if we could actually learn the features for the multiple object tracking problem, that is the cause. So all this information about appearance, about distance between bounding boxes. But at the same time, we would also learn to do data association. Essentially, we would learn to find a solution on the graph. So right now, we have presented the graph formulation, and this is completely separate from the learning of the cause, right? So these are two separate processes. Therefore, you can imagine that it's not really optimal, right? So the cause that we learn with the neural network are not really optimal because we're not seeing this graph structure. So what if we could actually exploit the graph structure and do learning, perform learning directly on the graph structure? So we would find a solution for our data association problem, and at the same time, we would find the best features that would lead us to the best trajectories. So this is what leads us essentially towards deep learning on graphs. And the idea is that we're going to move away from the classic domain in which we have been doing deep learning. So far we have worked a lot on images. And this is a very regular domain, right? So the order of the pixels is really important. It is important whether you have, for example, the eye and the nose at a certain location or whether the eye is really far away from the nose. So there is a certain regularity. First, the neighbors are always placed on the same positions. And second, the order is also important. So why am I mentioning this? Well, I'm saying this because when we actually try to apply our convolutions on top of the image, so essentially when we want to train a convolutional neural network, what we do with each convolution filter is that we slide it through the image. And this convolution filter has a certain shape, and therefore it imposes a certain structure. So the relationship of the weights that you can see here depicted in different colors is always the same. And what we're trying to find here with this convolution filter is exactly this relationship of weights also in the image. And we can do this because our domain, our image domain, is actually regular. So what happens when we jump into a new domain, for example, point clouds? So point clouds are very rich in information. We have the 3D point location of objects. We can even have point locations of entire cities that we can reconstruct. We can also assign semantic information to a point cloud. We can also have RGB values coming from an image, which we can also assign to a point cloud. So there's a lot of information that point clouds can contain, but there is one caveat, and this is that point clouds are irregular. So first of all, if we now take this rabbit with this point cloud representation, and for example, we rotate it, so we make a transformation to the point cloud, the rabbit will still stay the same. It will still be a rabbit. But now we will see the points in a completely different location. Another important thing is that the order of the points is not relevant at this point. So there is a certain permutation invariance that we would like to have on any operation that we actually apply to the point cloud. So I don't care if I actually analyze first the point at the nose of the rabbit or the point at the tail of the rabbit. I should always reach the same conclusion that, for example, this whole point cloud representation represents a rabbit. So you can see that this new domain is very different from the image domain that we're used to. Another domain that is very, very different would be, for example, a domain that is represented by a graph, as we can see here in the image. And this would be, for example, a social network or a citation network, where each node is actually a paper and each connection is a citation. So we can actually represent lots and lots of concepts with these graphs, where the nodes represent one concept, for example, a friend in your social network or a paper that you're actually citing, and the edges represent connections between these concepts. And actually, recommender systems, social networks, all have a representation that is based on these graphs. And as you can see, these graphs are also irregular, and we cannot readily apply convolutions, for example, on top of these graphs. So if we actually want to perform any kind of deep learning, if we want to do learning on top of these new domains, on top of point clouds or on top of citation networks, we need to come up with new tools for that. So it turns out that there has been a lot of work on deep learning on graphs, and these are essentially generalizations of neural networks that can operate on these domains that will now have a different structure, that will now have a graph structure. And the main idea is that we need to actually face two challenges. So first of all, we're going to have variable sized inputs. So before in the images, we had rather regular inputs that you can actually have any image size. But of course, the convolution has always the same shape. And thanks to the sliding window, it can be applied to multiple input sizes. But now we have a different challenge. Now the thing is that a social network can contain 10 nodes, for example, for 10 people with a series of edge connections, or it can contain 100 people. And we need to define operations that can operate on the graph with 10 nodes and 100 edges, and the graph with 100 nodes and lots of edges. And also, we need to have invariance to node permutations. So it doesn't really matter which node we're analyzing in the graph. We need to treat it the same way as all the other nodes. So the general idea of graph neural networks is that we're going to represent our concepts with a graph. And we're going to start by building this graph with optionally, but most likely we're going to have a series of node and edge feature vectors. These are essentially embeddings that contain certain information that you're interested in processing. And we will actually see quite some examples on what kind of information can you put in there, especially in the context of computer vision. Now, in the second step, what we're going to do is we're going to perform a series of information propagation steps. And these are essentially separated into several iterations. And the key idea here is that you can consider each update step or each of these information propagation iterations as a layer in common neural networks. And so essentially what that means is that in the first hidden layer, and this is again not actually a layer as we understand in CNNs, but rather an information propagation step. So in the first one, all the nodes are going to connect to the neighboring nodes and are going to gather information. Then we're going to move to the next layer, to the next information propagation step, and the same is going to happen. Of course, now your neighboring node has collected information already from the first step of its own neighboring nodes. So in practice, what happens when we reach the second information propagation step is that you are receiving information from a node that is 2 steps away. So the idea is that the further you go in your information propagation steps, so the more hidden layers you have in your graph neural networks, you're actually connecting with nodes that are further and further away. And when I actually say that you have established a connection with a faraway node, what I mean is that you receive some type of information through these information propagation steps, and this information is always in the form of an embedding. So after this iteration, after these information propagation steps, what you actually have in the output is a graph which has updated context-aware node and also possibly edge feature vectors, which essentially means that I haven't really made any decision here yet. All I have done is actually update the feature embeddings of my nodes and of my edges with information from my neighbors. And so now the interesting part, of course, is the information propagation step. So how does this actually happen, and how can I overcome the key challenges that I saw before? So namely that I can deal with an arbitrary amount of nodes and edges, and second, that my operations are actually permutation invariant. So let's introduce some notation. As I've said, we will start always by working on a graph, and the graph G has a set of vertices V, which are the nodes, and the set of connections or edges, which are E. Now we're going to denote the embeddings of our nodes and of our edges with the letter H. So H is for the embeddings. And these embeddings, again, can come from any network. It can be an embedding that you have manually defined. It can be an embedding that comes from a CNN that parses information of an image. It can be an embedding that comes from an RNN, anything at all that can be represented with a vector. And so we'll have the embeddings of our nodes, which are HI, and the embeddings of our edges, which are represented by HI, J. So here we'll denote also the step of these embeddings. So 0 means that these are the initial embeddings. As soon as we perform a message passing or an information propagation step, then this embedding is going to be updated to step 1, for example. So this is what we represent by HI superindex L. This means that actually the node embedding for our node I has been updated L times. So there have been L message passing steps that have updated the node embeddings with information from the neighbors. And again, the idea is that we're going to iterate through a series of information passing or neural message passing steps. So essentially what's going to happen is that my nodes are going to connect to my edges in one step, and in the second step, the edges are going to connect to the nodes. So at every iteration, what is going to happen is that my node is going to receive the features from the neighboring nodes. And this is going to happen through the edges. So here, let me play this again for you. This is a neural message passing step where the node actually collects the information from the neighbors. And so now the idea is that you have a varying number of neighbors. Could be that a node has 3 neighbors, like the node depicted here, but for example, the node here at the bottom has only 2 neighbors. And if I actually want to define a deep learning architecture that works for all the nodes in the graph, I need to have a feature aggregation operation that is actually, first of all, order invariant, and second of all, it can take any number of inputs. And the other interesting thing is that, of course, we need to put some learning into the pipeline, right? So aside from the aggregation of information that the node does, aggregates the information of the neighbors, this aggregation step needs to also include a learnable function, right? I want to know how to aggregate this information, and I want to know how to process it. And this needs to happen through, of course, a learnable function that I'm going to learn through backpropagation. So let's take a look in more detail at what is exactly a neural message passing step. So first of all, what we need to create is a message for each node. So in this case, we're creating the message for node V for step L plus 1. So I want to move from step L to step L plus 1. Now the first thing that I'm going to do is that I'm going to take my node V and I'm going to look at my neighbors. And these neighbors are represented by this letter U. These are the neighbors of V. And so what I'm going to do is essentially I'm going to gather the information of the embedding of my neighbors, my own embedding, and the embedding of the edges. Right? This is this aggregation step that we were discussing. And then I'm going to put a learnable function on top. And this learnable function can have any shape, could be, for example, an MLP. This is represented by this letter M. Now, the interesting thing here is that for all the nodes in the graph, this function is going to be exactly the same. So all the nodes in the graph are going to be processed exactly in the same way. So the thing is that I'm going to process this information, I'm going to process these embeddings, and then of course I have to do the aggregation step. So I have to actually collect all of this information into one single message. And for this I have to do an operation which is permutation invariant and which actually can work with any number of nodes which are neighbors to my node V. And what I do in this case is I just do a summation. So I sum all the information of my neighbors, so it doesn't matter how many neighbors I have, and it also it doesn't matter the order of my neighbors. So there is no natural order in the neighbors that I actually want to impose. I just sum all of their embeddings. And what I'm going to do, I'm going to create this message, right? Which is now kind of an aggregated embedding information. So after this, what I'm going to do is I'm going to update my own embedding, right? So I'm a node V, and I want to update my embedding with the information that I've actually captured from my neighbors, with this message that has actually gathered all this information. And for this, what I'm going to do is I'm going to take my own embedding at step L. I'm going to take the message, this aggregation of information, and I'm going to pass it again through a learnable function. And again, it's important to note that this learnable function, first of all, can have any shape, could be, for example, an MLP, could be a convolution, and that it has shared weights across the entire graph. So all of the nodes are going to be processed by the same function U. And so the interesting thing now is that we have separated neural message passing into 2 steps. The first step, which is the construction of the message, which is actually this aggregation step. This looking for information of your neighbors and aggregating them into a message. And in a second step, updating your own embedding. That is, looking at this information from the neighbors, looking at your own embedding, passing everything through an MLP, for example, and updating the embedding of the node V. Now, the interesting thing is that there's a lot of graph neural network types, a lot of models. We have graph convolutional neural networks, message passing networks, but most of them can actually be seen as a specific example of this formulation. And we're going to see a couple of these examples in this lecture. So let's see a first example with a specific definition for the message passing steps for the operations that will actually be performed on our embeddings. So the first one is this creation of the message. So the idea here is that there is the node V, and the node V looks at the neighbors, which are represented by the letter U, and looks at all the embeddings of the neighbors. These are represented by these embeddings here. And essentially what it does is it performs an average operation. Again, permutation invariant operation, and I don't care how many neighbors do I have because I'm going to perform a normalization step here. So if I have 30 neighbors, I'm going to take all of their embeddings and I'm going to average them. And with this operation, I've now created the message for my node V. Now the second operation is the update of the embedding of node V. So the idea here is again that I need to combine the new message that I've actually retrieved, so all the information of my neighbors, with my own previous embedding. And this was the embedding at step L. And how I'm going to basically combine these two sources of information is actually with learnable matrices, right? I don't want to actually decide whether the new message is more important than the previous embedding to compute the new embedding, but I actually want to perform an operation with learnable weights. And for this, I'm going to have these two learnable matrices, W and B, and these matrices are going to multiply the new message and are going to multiply the previous embedding, respectively, to actually create the new embedding. And on top of this, of course, I'm going to have a nonlinearity. So look at the similarities already, for example, with an MLP or with a convolutional operation. So what I'm doing is I'm getting from the previous layer certain information. I'm processing it with learnable weights, which is what we do for any of the operations inside an MLP or inside a CNN. And then I pass it through a nonlinearity. Same thing here. And so the really cool thing about this formulation is that it's very general, right? So these weights that we're actually multiplying with our message and with our previous embeddings could be anything, could have any shape. We could have an MLP, or we could have a recurrent neural network. We could have any kind of operation we want in there, depending on what is the shape of our message and what is the shape of our embedding. And again, the important thing here to note is that, for example, if we use an MLP, like in this case, MLP1 is going to act on all the messages of all the nodes in the graph. So this is going to be an operation that is going to be applied for all nodes. So it's going to have a huge amount of share weights. And the same happens for MLP2. So it's really important, this is really an important characteristic of neural message passing networks or graph neural networks. And that is that all the operations that are applied on a node or they're applied on an edge are exactly the same for all nodes and edges of all the graph. So it's like huge Siamese network for all nodes and edges. So let's look at another example. Let's look at the famous graph convolutional networks. So what are really graph convolutional networks? And we will actually see that graph convolutional networks are can also be written inside the formulation that we have presented at the beginning. So let's start as always with the aggregation step, with the creation of the message. So what we're doing right now is we're looking again at node V. We're looking at the neighbors of node V, which are U, but we're also looking at the node itself. So before, what we did was, when we created the message, we ignored the embedding of the node itself. We said the message will just contain information of the neighbors, and then I will put it together with my embedding later on. So what we do in graph convolutional networks is we also take into account the node itself. So there is this notion of a self loop here, that there is a connection between the node and the node itself. And of course, now we have to really change a little bit the notion of normalization. So normalization is also going to take into account its own node. And so we're going to have a per neighbor degree type of normalization. But essentially, it is the same as we did before, just an aggregation step where you gather information from your neighbors, and in this case, from yourself. And so now the idea is that instead of having two matrices, one that acts on the message, that is on the neighbor information, and one that acts on your own embedding, your own node embedding, you can have one single matrix, right? Because we have already taken into account the embedding of the own node V. So now we need only one matrix, which is going to be the same learnable matrix for self loops, for the own node connection, and for the regular neighbors that are connected to the node. But essentially the idea is the same. I'm going to perform an operation which multiplies weights by my messages and then passes it through a nonlinearity. And so this matrix of weights is going to have size, number of channels that we want in the output, multiplied by the number of channels that we want in the input. Again, it doesn't really matter how many nodes are connected to the node V, right? So the number of connections doesn't really matter. The only thing that matters is that I have a certain embedding representation with certain number of channels, and now I want to convert it with an embedding representation H, which can actually fit as the embedding of my node V. And so essentially, what you want to do is you want to collect information from your neighbors. This is the aggregation step. And you want to transform it through a learnable function into a new embedding. So this is not really much different from what we do in normal convolutional networks, right? So we also have certain embedding, certain feature map, which we want to transform into another feature map. But here the trick is that unlike a normal image convolutional filter, the neighbors are, again, not regular, right? So the image space is regular, so we can define convolutions that are, for example, 3 by 3, and we know that we will be able to apply them all over the image. But here we don't know how many connections a node has. So what I first have to do in order to apply a convolution type of operation is, first of all, I have to do this aggregation step. I have to do this permutation invariant operation so that then I can apply my set of weights and I can apply it to a certain specific embedding size. So again, the operation is first the aggregation of information, which allows us to have and to deal with any number of connections. And the second is an operation that mimics the convolution operation. So far we have talked only about updating the node embeddings, right? We haven't really done anything with the edge embeddings. And it is true that the framework that we have presented so far is only suited to actually learn node embeddings. But the question is, what if we're actually interested in the edge features? What if the information that we want to recover is in the edges and not in the nodes? So this, of course, depends on what you want to get from your graph neural network. But if you want to learn node embeddings as well as edge embeddings, you have at least two options. So first of all, to work on the dual graph so that you're actually updating the edge embeddings instead of the node embeddings, or a formulation that we will present now, which is actually more general, where you can do alternating node updates and edge updates. So let's see what this new formulation is about. So the more general framework consists in actually 2 steps. So we start from the initial graph that we had already before, with the node embeddings in yellow and the edge embeddings in green. And now what we do is, instead of doing an aggregation step where the node collects information from neighboring nodes, what is going to happen is we're going to divide this propagation process into 2 steps. The first step is a node-to-edge update, that is, the node communicates with the edges that is connected to and passes along the information of the embedding. And in a second step, the edge contacts the nodes that it's connected to. So now we have basically divided this propagation process into 2 steps so that both node embeddings and edge embeddings are actually updated. And so essentially, what is going to happen now at every message passing step? So first of all, we're going to do the node-to-edge update. And the node-to-edge update basically means getting the embedding of node I for the previous message passing step, right? So I'm looking at the node I. Then I'm looking at the embedding of the edge ij, which is actually the embedding that I'm interested in updating. And I'm looking also at the embedding of the node j in the previous message passing step. So essentially, for an edge ij, which is connected to node I and node j, what is going to happen is it's going to look at its own past embedding, the embedding of the neighboring node, and the embedding of the other neighboring node. And it's going to gather all this information and it's going to pass it through a learnable function, which again can take any shape. So this is the step where actually the nodes make contact, pass information to the edges. So we are passing information from the yellow node embeddings all the way to the edge embedding. And the only thing that we're updating in this step are the edge embeddings. Now again, it is important to note that we're going to do this update information by passing it through, again, a learnable function. And this learnable function updates actually all of the edges in the graph. So after one round of node-to-edge communication, the edge embeddings have been updated. So now essentially the edge embeddings contain information about the pair of incident nodes, right? We have taken the information from ij and we have passed it to the edge ij, which actually connects these 2 nodes. So now we go for the edge-to-node update. In this update, the edge embeddings are going to be used to update the nodes. So the opposite operation. So in this case, of course, we have the same problem as we had before in the first formulation, and that is that I don't know how many nodes, how many edges are connected to a node. So if I have to update the embedding of node I have to look at all the connected edges, and this could be of an arbitrary number. It could be 3 edges, like for example is in this case, but it could be also 2 edges, like for this node here on the bottom left. So again, I need to define an order invariant operation that can take in any number of nodes. So I'm going to take the embeddings of all the connecting edges to my node I, and I'm going to perform this order invariant operation to create again the message of node I. And once I have this message, same as before, I can, for example, concatenate it with the hidden state of the node in the previous time set, pass it through a nonlinearity, and then update the embedding. So again, this aggregation step and this passing through the nonlinearity, what it's going to do is going to update the node embeddings, and it's going to add contextual information about the neighbors. So this is very similar in spirit to what we had before, just that now we divide it into 2 steps. First updating the edges, and then the edges update the nodes. So just a few remarks to kind of settle some important ideas here. First of all, the main goal when we're actually performing these message passing steps, or when we're actually training our neural network, our graph neural network, is that we want to obtain node and edge embeddings that contain this context information that basically implicitly encode, first of all, the graph topology, so who is the neighbor of who, and that it actually contains also neighbor feature information. So if I'm a node, first of all, I want to learn about my immediate neighbors, and I want to encode their features. I want to know what are they actually seeing and what are they actually processing. And the only thing that we do when we actually perform the message passing steps of a graph neural network is to pass along the information in the graph. So after doing the node and edge updates, for example, for L steps, and this is something that you have to define, how many steps do you want to do, how many message passing steps do you want to perform? So after all of these steps, each of the nodes and also each of the edges, it's going to have an embedding which contains information about all the other nodes which are at distance L. And this is important, right? So again, we have this notion of layers inside a CNN and going deeper and deeper. And here each layer consists of one message passing step. So each time we perform one message passing step, we go a little bit further and we gather information from nodes which are one step further away. So if we perform L steps, we will have received information from nodes which are at the distance L. And all of the operations that we have defined are differentiable. This is really important because actually we can train these architectures in an end-to-end fashion. We can actually perform backpropagation. So we can train this as we train any other CNN or any other MLP. So as a last important point, there's actually a really large literature on different types of graph neural networks, different models, different operations that you can do for each of the update steps. I would recommend actually for you to take a look at the paper that we have cited for an extensive review of a lot of these models. So if you want to actually see what type of MPN models, what type of message passing network models there are out there, I would recommend that you actually read this paper. So now we go back to our initial problem, right? And we want to see actually how can we use these message passing networks to actually solve the multiple object tracking problem. So this is what we actually propose to do in one of our most recent papers presented at, or will be presented actually at CEPR 2020. And this is actually how to leverage message passing networks for the task of multiple object tracking. And here the idea is that you have your detections, your bounding boxes as input. And the first thing that you do is you construct a graph and you actually encode appearance and scene geometry cues into the node and edge embeddings. So again, these node and edge embeddings, which are just these vectors, they can come from anything. In our case, they come from a CNN representation that encodes the information of the detection. And we also have some scene geometry cues, like for example, encoded in the edges is how far away are two detections in the image space. So once we have created this graph, once we have decided what is going to be the initial embeddings for the nodes and for the edges, we do a series of message passing steps. And as we have seen, these message passing steps essentially means that nodes communicate with edges, edges communicate with nodes, and essentially all of the information of the different bounding boxes, the different detections, is propagated across the entire graph. And once this is done, what we can do is we can directly put, for example, an MLP on top of each edge, And we can actually start by classifying edges. So we classify edges into active connections, which means that actually the two nodes that is connecting belong to the same trajectory, or inactive connections, meaning these two bounding boxes have nothing to do with each other. So essentially, in the first step, we have constructed the graph. We have then passed along the information. Detections have been connected to other detections. And in a third step, now we are able to robustly classify the edges into active connections or not. So essentially, if we want to map it to traditional CNN, let's say, view, we can consider the graph construction and the feature encoding as sort of a feature extraction step, and the neural message passing and edge classification as a learnable data association step. So let's look a little bit more into detail at how do we actually perform these feature encodings, right? So what we want to do is, first of all, we want to encode appearance information. And appearance information is directly linked to a node. Each node represents a detection, and therefore what we want to do is we want to take that patch of the image that represents a pedestrian, we want to pass it through a CNN, and we want to obtain an embedding that we're going to put into the node. So we're going to do this for all the nodes in the graph, which represent all the detections that we have detected in our step 1. And then we're going to put some geometry information on the edge. And by geometry information, we mean, for example, what is the distance in time between the two bounding boxes? What is the relative box size? What is the relative box position? Now, the idea here is that a pedestrian moves in a smooth way from one frame to the next in a video. So it is not really realistic to assume that the pedestrian will have moved from the top left of the image to the bottom right in just one frame. So this is a little bit the type of information that we're trying to encode here. We're trying to give the graph neural network this information so that it can make the appropriate decisions. So that if it sees two detections which are, for example, one frame away, but really, really far away in the image space, then it knows that it's not very likely that these two detections belong to the same pedestrian. Now, again, important thing here, the concept of shared weights. So the CNN that is going to extract the information for the node is going to be the same for all nodes. And the MLP that is going to process the geometry information is going to be the same for all edges. So again, very important characteristic of graph neural networks. So once we have defined our initial embeddings, now the goal is to propagate these embeddings with the message passing steps that we have seen before, with the node to edge updates and with the edge to node updates. So essentially, the new embeddings, what they're going to contain is they're going to contain higher order information among detections, right? You're going to look at detections which are several frames away, and you're going to decide whether these actually represent the same person as you, as the node, or they represent another person. And by looking several frames ahead and several frames behind, you can actually make a much more informed decision. Now, in the paper, we also include a new type of message passing step, which we call time-aware message passing step. So you can see on the left the classic message passing step depicted, which actually takes a node that we're analyzing, in this case node V, looks at all the neighbors in the future and the past, collects all this information, right, does this aggregation step, and then passes it through a series of learnable functions. So this is the normal message passing step. But what we actually propose to do is we propose to treat past connections and future connections in a different way. So intuitively, the connections between frame t and t-1 should be treated separately than the connections of frame t and t+1. So the idea here is that for this node here, you will actually have one neighbor at frame t-1, which is going to represent the same person, and one neighbor at t+1, which is going to represent the same person. So you want to separate the two operations. So essentially what we do is we perform a different aggregation for the past connections, the connections between t and t minus 1, and the connections between t and t plus 1. And by doing this operation, we allow the network to have a notion of time, to have the notion that the connections to the past and the connections to the future should be treated separately. So now we're going to the last step, right? We haven't really discussed this in the lecture. We have just discussed the message passing steps. So it's very nice to pass along information. It's very nice that now your node embeddings and your edge embeddings contain this higher order information, this information of the neighbors. But it's now time to actually target our task, to actually perform, for example, classification. And in the case of multiple object tracking, what we're interested in doing is classifying edges. So we want to know whether the connection between two nodes is actually an active edge, which means that these two nodes represent the same person, and therefore you want to create a trajectory, or the connection should not be active, which means the two nodes represent two different people. So essentially what we want to do is we want to perform edge classification into active and inactive nodes. And for this, we can easily train with a binary cross-entropy function, like we have seen for most of our classification problems. But now what we're classifying are edges. So we're looking at these updated edge embeddings after all of these message passing steps. And from here, we want to obtain a decision. With an MLP, we want to obtain a classification, yes or no. And these are going to be essentially the edge predictions that we're going to get, for example, from a sigmoid at iteration L. So of course, first we need to perform the message passing steps, and at the end of the message passing steps, we look at the embedding and we make a prediction. And in our case, we also have this weight, which actually balances active and inactive edges. So we have the problem that, of course, most of the connections are inactive and there are just very few connections which are active. And this is actually a weight that we need so that we give enough importance to active edges so that the message passing network can be trained properly. And finally, what we're going to do is we're not going to only compute the prediction loss at the last step of the message passing, but we're going to make this edge classification for each of the last, for example, L message passing steps, and we're going to aggregate these predictions. So essentially what we do is we perform a total of 12 steps, for example, 12 message passing steps. So after 7 message passing steps, what we're going to do is we're going to start to make edge predictions. And we're going to accumulate these edge predictions at step 7, step 8, 9, 10, 11, 12. We're going to accumulate all these predictions and sum them up in the loss. And this is essentially to get a stronger signal for learning. But we actually have to differentiate the training procedure, which means accumulating predictions for the last L steps, with the testing procedure. And the testing procedure, what it simply does is it performs 12 message passing steps, and at the end, we make the prediction. But it turns out that with our proposed time-aware updates, around 98% of the constraints are automatically satisfied. So with a simple rounding, which takes actually negligible time, we can actually obtain constraint satisfaction and integer solutions. And this is because essentially we have put all the structure of the problem into the learning with this time-aware updates, which treat past nodes and future nodes in a different way. Now, overall, our method is fast, so it runs at 6 frames per second, which is a magnitude faster compared to other graph methods, and it also achieves state-of-the-art results in the mod challenge benchmark. So this paper has really been a strong push forward for the tracking community to actually start to do learning in the natural mod domain, which is actually a graph domain. Okay, so in order to end the lecture, we will talk about MOT evaluation. So evaluating multiple object tracking. How do we actually do this, and what kind of benchmarks do we actually use? So it turns out that there's a set of metrics that we're going to use to actually evaluate multiple object tracking. So first of all, the first thing that we need to do to evaluate the results is to actually match our prediction, match our trajectories with ground truth trajectories. And in order to do this, we will use exactly the same Hungarian algorithm as we have been using to match detections of frame t with detections of frame t plus 1. And for each frame, what we're going to compute is we're going to compute a match between our predictions and our ground truth trajectories. And this is going to give us a set of false positives, a set of false negative, which means detections which we have actually missed. And it's also going to give us identity switches. So identity switches is essentially what really measures the tracking performance, because here we're measuring whether we're assigning two different identities to a single ground truth trajectory. Once that happens, then we have an identity switch. So the computation of identity switches is actually not so trivial. So we can have actually different scenarios in which identity switches can be present. So here we have, for example, these three scenarios. The first scenario, we have the ground truth trajectory here as a dotted black line. And then we have two trajectories predicted by our algorithm. We have the red trajectory and we have the blue trajectory. Now, on a frame-by-frame basis, what we're going to do is we're going to match detections with our Hungarian algorithm. So we're going to match our predictions with our ground truth. And here in gray, we depict the threshold. And if a prediction falls within this threshold, then it's considered to be a match. So what is going to happen is we're going to have three detections which are matched with the red trajectory. But then the red trajectory deviates, and therefore we have the blue trajectory detection, which is matched with our ground truth. So essentially what has happened here is that we have covered one ground truth trajectory with two predicted trajectories, the blue and the red one. And of course, at this particular frame transition, so between frame 4 and 5, you see that the identity that was assigned here at frame 4 is different from the identity assigned at frame 5, and therefore we have an identity switch here. Now this is the first case where we can have an identity switch. The second case is depicted in this case labeled B, in which we have two trajectories, the red and the blue one, covering the ground truth black trajectory, but in the middle we have a fragmentation. A fragmentation usually means a lack of coverage of the ground truth trajectory. And in this case, we could have a fragmentation as well as an identity switch. And another source of identity switch could be the third one depicted, in which we would actually have two trajectories which are overlapping each other quite a lot. And it turns out that our predictions here make a mistake, and therefore they kind of cross each other. And therefore, effectively, what is happening is that the blue trajectory is coming closer to the ground truth red trajectory that we had at the top. So in theory, what could happen is that the red trajectory starts being matched with the top ground truth trajectory, and then suddenly is matched with the bottom ground truth trajectory. So this would create a kind of a false identity switch, right? Because the red trajectory is still close enough to the top ground truth trajectory. So here, basically, each evaluation method is different. What we decided to do in Mod Challenge is we decided to keep identities consistent. So as long as the detection is within the threshold to be matched, we're going to match it to the detection that doesn't create the identity switch. Therefore, even if the blue trajectory is closer to the ground truth in this case, we're still going to match the red trajectory in there so that we don't obtain any identity switch in this case. Of course, the blue trajectory is not matched to anything, and therefore a false negative is created. So even computing identity switches is actually kind of a controversial issue. And there are different methodologies, different kits, different evaluation metrics that compute identity switches in different ways. This is actually the way that we use at Mod Challenge to compute identity switches for all the methods that submit to the benchmark. So again, we can count actually an identity switch because the ground truth stack is assigned to two different predictions. You can count both an identity switch and a fragmentation if the identity changes within a ground truth trajectory, but at the same time you're losing track of some of the detections in the frames in the middle. And the last scenario, the identity is actually preserved even if two trajectories would actually overlap with one ground truth trajectory. So if this happens and both trajectories, both predictions stay within the matching threshold, then we're going to choose the one that allows us to have the least ID switches possible. Okay, so with this set of metrics, with this set of measures, false positives, false negatives, which are at the level of detections, and then with identity switches, we can actually create the metric that is called the MOTA, the multi-object tracking accuracy. And this essentially consists on summing the false negatives, the false positives, that is the detections that you have missed, the detections that you have created when there was actually no object, plus the identity switches. We sum up all of these quantities and we normalize it by the number of ground truth detections. And 1 minus all this term is what is called the multiple object tracking accuracy. Now, the other thing that we need actually to define is what kind of data sets can we work on if we're interested in the multiple object tracking problem. So our own data set that we introduced in 2014 is called the Mod Challenge Benchmark. And this is actually for people tracking. And we have several challenges from less to more crowded. We're introducing now challenges also of tracking not only people, but other objects, such as, for example, interesting objects in biology. We're introducing challenges for segmentation and also a lot of future challenges. So stay tuned if you're actually interested in multiple object tracking. And then we have other benchmarks, such as the Kitty benchmark, which is very well known for autonomous driving and so very much used for vehicle tracking, or also UAD track, which is also for vehicle tracking. These are just some of the data sets. So there are other data sets that you can use actually for multiple object tracking. Okay, so with this, we reach the end of the second lecture on object tracking. Today, we focused a lot on multiple object tracking. Thank you for your attention and stay tuned for the future lectures.